Hello, hello. This is the start of the 7:45 a.m. Okay, the 7:45 a.m. recording for Wednesday, May 6th. Okay, all right. Good morning to y'all. Let me move this over here. I have a couple windows open just to get things going ready for today. We'll start with a round of announcements. I will repeat announcements at the end of class. Um, Today's Wednesday, but I'm just putting this here as a reminder that there is an online quiz, the last online quiz tomorrow on Thursday. So please keep an eye out for that. Start WebWork 44 today. That is going to be the last one. Um, I would suggest starting it today. If you can get it done today, great. Then you can just be done with it all. If you're stuck, then there's still office hours, of course. But if you put it off till the day it's due, well, the due date for it is, I mean, in order to have it have any role, really, I had to make it due before the final exam opens. So um, there are really two assignments that are both extra credit that are due next Monday during the start of finals week. I would just start WebWork 44 today, so you don't have to deal with it, or you can just wrap things up. Here's office hours for the rest of the semester, all listed. If these times don't work, send me an email. We'll set up an appointment. Um, the final exam, you need to choose a 6 hour block of time in which to work on the exam somewhere between May 12th and 13th. I have not gotten around to it yet, but later today I will be posting practice materials for the final. Okay, so where did we leave off? Yesterday, we had seen this thing, and it'd be good to just repeat this as a reminder. We saw this thing called the area between curves. So if you have f of x is greater than or equal to g of x, that is, the graph of f is above the graph of g, right? So f always stays above the graph of g, at least for all x values between a and b. Then the area between the two graphs from x equals a to x equals b is given by this integral. So you set up a definite integral, and what's the function you're integrating? It's actually the first function minus the second, or I mean the upper function minus the lower function. So we saw that yesterday, and just as a reminder here, f of x greater than or equal to g of x, really just geometrically this means that the graph of f is above the graph of g. And as a reminder that, well, if this really does happen, so if you're applying this formula in a situation where f is greater than or equal to g, then f minus g is bigger than or equal to 0. And it involves a property that I don't want to dig into too much because we didn't here, but it turns out that due to something, then computing the area between curves using this formula, you're always going to get a positive area, even if that region is below the x-axis. When you do upper function minus lower function, you take an integral, you always end up with an area positive, which will be unlike what happens. Um, That'll be unlike what happens when um, when you just integrate a single function, there's this concept of signed area. It seems strange that it works out that way. There's some details I really don't want to dig into too much in a class setting. You could certainly ask about it, and we can kind of go over some of those details. But yeah, so integrate a single function. You're talking about signed area. Integrate upper function minus lower function. You always get a positive area. I previewed this at the end of yesterday. But today, the big goal is to talk about what happens if one curve isn't always above the other, right? So that's the requirement here, is that f of x has to be above g of x for all the x values from a to b for which you integrate. And if that doesn't happen, there's actually a very nice solution to it. Just split up the problem. Split the problem. So before doing that, just let's just warm up with a question that could have been asked yesterday, just as a first question of the day, just to make sure we're reminding ourselves. So I'd like to set up an integral. So we're not going to compute all the way down to having a number. We could, but let's set up an integral as a review of yesterday to represent the area between y equals x squared minus 2x plus 4 and y equals 2x plus 9. So even in terms of a rough sketch, I want to, we will look at some graphing tools to help clarify things, but like I want to just really point out how much you can get done without relying on technology first. You have over here a parabola, yeah. There's that x to the second power, so that's a parabola, and you have over here a line. You actually have a concave up parabola, right? And you have a line, or more specifically, you've got a concave up parabola and a line of slope 2. So in situations like this where it's just the area between these two regions. I mean, where is the origin located compared to, well, the origin's at the origin, but where's the parabola located in comparison to the origin? I don't want to typically worry about those details if I can avoid thinking about those things. So I just, sometimes without even drawing axes, I just leave this out, right? So just leave out the axes. Sometimes I just draw that concave up parabola, draw a line of positive slope. Again, my line here looks like maybe slope is 1 when in actuality the slope should be 2. But this is enough of the picture, right? It gives this idea that there's this region here. And at least for that enclosed region, right, the area between these two curves, the line is the one that's above. Like, so what I mean by the line is the one that's above is if you start somewhere in the middle of this shaded region. Let me try to erase a little bit here. Oh, that was technology a little too much erase. So if you start somewhere in the middle of this shaded region, I've intentionally not fully shaded it right now so I can demonstrate, and you move upward, you end up hitting the line, right? So that's I didn't fully shade the region so that I could demonstrate what I'm doing right now, but the upper part of the shaded region is the line, and then if you start somewhere in the shaded region and you travel south, you travel down, you end up hitting the parabola. So in this case, the line is the thing that's upper, and the parabola is the thing that's lower. Had we been talking about like this region over here, that would have been a different story. I mean, then the parabola would have been the upper, and then the line would have been the lower thing. But in this case, because we're talking about this enclosed region, the line is above and the parabola is below. Okay, yeah. So in the region enclosed by the parabola line, the line is above, the parabola is below. And so already we can set up almost all of the problem. Like in just just this much of like, okay, the line is above, so that's the upper function, upper minus lower, so that what we integrate here is so that what we have there is always positive is what we want to do. In fact, all we need to do left is find the x values. Right? So this is what I mean by rough sketch. You don't have to like draw that parabola all that accurately. We didn't even place it on axes so that we saw exactly where in the plane it was. It was just, there's a concave up parabola, there's a line, a little rough sketch. You can see that the line has to be above the parabola. We need these two x values though, and just to show a picture, make sure just to confirm what's going on. Looks something like this, right? So we're talking about this shaded region in purple, and so I'll use the mouse cursor to do this. That like if you move up, what cuts and creates the top of the border of the shaded purple region? It's the blue line, right? This blue line here is what's upper. And then if you start somewhere in the middle and you travel downward because you want to see what's lower, what ends up being the thing that cuts and like stops the purple thing, that ends up the lower curve ends up being the red thing. Here it's the parabola. Okay, what we need are the x values, and we can kind of maybe squint and see that maybe the x value is 5, maybe the x value is -1. But, you know, we could probably even use this to really check by clicking. But the point is, what? How could we find the x values without relying on on this? And we saw that idea yesterday, right? So I showed the picture and all, yeah, but like we could finish this off without relying on the tool for those x values. So I don't want to use that. I want to let's use our algebra to find the x values where the red and the blue curves intersect. We need to set the y's equal. So we'll take the two given y's in the question, set them equal. And if you take a look at this equation, it's a quadratic equation. I mean, maybe it's a little messy because there's linear terms on both sides and whatever, but let's add and subtract things on both sides. I would like to let's get a 0 on the right side. So how about subtract 2x on both sides and subtract 9 on both sides? Then you should end up with x squared minus 4x minus 5 equals 0. I factored that. I factored the left side, left the right side alone, and you should have x plus 1 quantity times x minus 5 equals 0. So you can set each of the two factors equal to 0. X plus 1 equals 0, x minus 5 equals 0. And then solving the individual equations, you have x equals -1, x equals 5. Now, sometimes the order here might be swapped. It just depends on what order you wrote the factors in. So the smaller number, the smaller x value should be the lower part of the integral. So -1 to 5. Okay, so I hope that works just as like just a review of what kind of thing we looked at yesterday. Right. So, and what we could now find the number that's associated to this. We'd have to first look at the indefinite integral and then find an antiderivative and all that. But just like yesterday, I want the major goal to be just talking about setting up an integral. The integrals that we are setting up, as far as could we go through the computations and find those integrals, they're really not bad. Like the indefinite integrations, the antiderivative problems that come up don't even require substitution. Right, so they're like you've seen worse integrals like in the last take-home exam. So I hope that looks okay. The thing that's going to be different is we'll change this up by looking at a question like this. So this one's not too bad, I promise, but it's a little different. So find the area between y equals x over 3 plus a 6, and then y equals 10 minus x over 3, and x equals 1, and x equals 9. Now, I know maybe the way this is written looks a little funky, but if we just use algebra to write this just a little differently, 1/3 x plus 6, right? That's a line, right? That's a line. Slope is 1/3, y-intercept is 6. The other one here as well, you could write this second line as bring that 3 in the denominator. It's still a 3 in the denominator, but just kind of separate the x. If you want, think of it as like there's this fraction 1/3 and bring the x. So, and then this second one, if it's helpful to you, swap the order of the terms. The negative should still be in front of the -1/3 x, the 10 after. And the point is, this is also a line. It is y equals mx plus b. So you've got a line of slope 1/3. You have a line of slope -1/3. You have a y-intercept of 6. The other line has a y-intercept of 10. And then x equals a number, that's a vertical line. X equals a number, that's a vertical line. So just as an inventory, like we have not actually completely drawn a picture here, but I'm just talking through the picture in words. We have a line of slope 1/3 first. We have a line of slope -1/3, and we have two vertical lines. I could already draw like a very, might not be totally accurate, but like with this, you can imagine actually a lot of the picture. And let's just go ahead and do axes this time, right? Like this is not too bad to graph 4 lines. So like look, a y-intercept of 6, slope 1/3. That's kind of shallow, but positive slope, right? So I'm gonna like something like that. The next line had a y-intercept of 10, but the slope was -1/3, so still shallow, something like that. roughly speaking. X equals 1, probably right over here. X equals 9, well, I don't know where this intersection occurs. It turns out that it is later. So it turns out that 9 is over here, but how did I know? Let's look at a picture that's graphed for us carefully first, and then we'll talk about it. Okay, again, this is a first one, so um, some of the things that we're talking about are maybe a little out of order from what you'd actually do when you practically solve a problem. But I need to get your feet wet. We'll just do this, right? Um, so let's just say that we got for free that the computer graphed for us the line of slope 1/3, the line of slope negative 1/3, the vertical line x equals 1, and the vertical line x equals 9. And you'll see that there's these two shaded regions here, right? The issue, it's like a bow tie. I should have dressed up a little more or something. Right? Okay, so ridiculous nonsense here. So the thing is, there's this first purple shaded region, and yeah, I should turn that off for a moment, right? So we see where the bow tie is, and maybe without shading, you see that like in this, it's really two triangles, and in the left triangle, the blue curve is on top and the red curve is below, and in the other purple region, this other triangle on the right, the red curve is on top and the blue curve is below. And so what matters is where they cross each other. Where does the red and the blue intersect? And in the slides, I mean, we see just here using the graphing tool that appears to be x equals 6 down here on the x-axis. But again, let's just talk about what we would do without the use of this tool. So for the sake of the slides, that unknown x value here, I've just called this C, just for a moment, just so that we can talk through. Um, so, but the whole point is like, let's even without the tool, I would say like, okay, from starting at x equals 1, which is where we ought to start, up until where the two cross each other. So I just called that x value C. Um, this line should be of that line. I mean, the line which had the higher y-intercept is gonna likely be the one that's above first, right? The bigger y-intercept. It has a head start, and then at the moment that they cross, starting at that x value, and then leading up to 9, probably again is then they swap which line is above. So before doing anything else, and just to make sure, I mean, this is a bit of a guess without the use of the graphing tool, but we should try to figure out where these intersect, right? That's the key, and that, I mean, it's the same deal really as what we just did in the last problem for a different reason, because we're going to split this up into two problems, but the same general idea is where do these two curves intersect? Set the y's equal to each other. So set this x over 3 plus 6 equal to the 10 minus x over 3. I added x over 3 to both sides to offset the minus x over 3. Subtracted 6 on both sides. There's a couple ways to attack this, but I just decided why not one easy option anyway is multiply both sides by 3. So you have 2x equals 12, and then divide both sides by 2, so you have x equals 6. So that's that middle point, right? So like in the picture, I would say like actually it makes more sense to go, okay, there was one line had a y-intercept of 6, right up here. This 6 is coincidental. That's an x equals 6. The other line had a y-intercept of 10, so positive slope, negative slope line, something like that so far, and then starts at x equals, well, actually I wouldn't even draw in where the x values start first. I would just put in this intersection, just because that's a thing we know here. So x-intercept, sorry, or the place where the two lines cross each other is at x equals 6, and then to the left of 6 is 1, to the right of 6 is 9. That region and that region. I'll actually just draw those lines solid, but like the point is there's two regions. So that this to me would sort of be the process of sketching and seeing what's going on without the use of the tool, and then this tells us kind of all the things we want, right? So we have an integral from 1 to 10, sorry, excuse me, from 1 to 6 of the line that had the larger y-intercept first minus the line that had the smaller y-intercept, the one that was below. And then the integral from 6 to 9, you'll notice the functions have swapped places because now it's this one that's above, right? It's a question each time of which thing is above and which is below. So in terms of implementation, maybe sometimes this is some work, but in terms of concept of what's going on, I don't think it's too bad. That the basic idea here is if one function is not always above the other, the formula we saw doesn't apply directly, but you can split up the problem, make several integrals. So like we use the formula once, and then in a separate region, the other function was above, and then we used that the area between curves formula again. So let's take a look at another one, unless there's questions on this one. Again, I think more than anything, it's a little hard to keep track of all the things when the picture keeps falling off screen. So let's try this all together. Find the area between y equals x minus 8 and y equals 4 minus x squared from x equals negative 8 to x equals 6. So again, I'd like to just do a general inventory of what we have here first. We have a line with slope 1 with this y equals 1x minus 8. We have a parabola that's going to be concave down due to, well, the negative in front of x squared, or you can see the concave down by taking a second derivative, getting negative 2, a negative number, so concave down for that second derivative. And then let's, even right away, then I would say we could draw a picture, right? Line of slope 1, concave down parabola. So it says area between this, and it didn't stop there. Like sometimes that would just mean we would just find this region in between and call it a day. But it did give us these x values. So where are those x values in relation to these two crossings, the two places where the parabola and line meet each other? Is this x value here on the right? Is that bigger than 6? Is that smaller than 6? I mean, there's a lot of questions that I still have about where to draw this vertical line x equals 6. I mean, does this line get drawn like to the right of this crossing or to the left of this crossing? Not sure yet, right? So I don't want to draw too much into the picture yet until we figure out more. What I want to do is actually let's do some algebra. I'm trying to do the process so that it looks more like what you would actually do is let's take these two curves and set the y's equal so that we can see where the intersections are first. And then when we know what x value occurs here and here, then we'll be in a better position to draw in the two vertical lines that we need to draw in. So let's find the x coordinates of intersection first. Set equal x minus 8 from up here, given in the problem, and 4 minus x squared. There's a quadratic equation. I would prefer to have a positive sign in front of the x squared, so let's add x squared to both sides. So x squared plus x. I wanted, at that point, if we're going to have an x squared on the left side, then maybe all the things should be on the left side and have a 0 on the right side. So I had to subtract 4 as well. The left side will factor as x plus 4 times x minus 3 equals 0. So you have x minus 4, x equals negative 4. Or x equals positive 3. Okay, so we can now update the picture so I'll just redraw here with this information showing. So yeah, here we go. So we had, there was this line of slope 1. Sorry, I'm having some little technical, okay. Line of slope 1, concave down parabola, right? And these two x values, well, okay, so there's two locations and two intersections, and of course the one that's more on the left, that's going to be the smaller x value. So this point, its x coordinate is negative 4. What's the y coordinate? We could figure that out if we want, but that point here has an x coordinate of negative 4, a y coordinate of, I'm not actually all that worried. It's not going to, we could find the y coordinate, but we're not going to need it. This point over here has x coordinate 3. So 3 comma, oh geez, okay, 3 comma whatever the y coordinate is. And then we can now, like, talk about this x equals 6, that vertical line, well, it's got to be to the right of this 3, right? So over here there's a 3. Oh, over there, x coordinate 3. So x equals 6 is further to the right. So, maybe over here. And you know what? Sometimes if this parabola is not drawn enough, just draw more of it. I mean, sorry for straightening out the picture. The parabola stays curved, but just enough to, we're faking out the picture a little bit, just enough to be able to draw in this vertical line x is equal to 6. And then there was this other vertical line x equals negative 8. Well, we have over here, let me move the mouse so that I can highlight. We had x equals negative 4, so x equals negative 8 should be somewhere to the left of that. So maybe, I don't want to go too far to the left because, see, like even how I drew this parabola, look, it eventually has to cross the line. It eventually does because, like, if you draw a t-chart out for a parabola, you plug in any x value, you're going to get a y value eventually. So the picture may not be totally accurate. Like, maybe this parabola is supposed to curve more or something, but it, we've rough picture, but it's here. And so the area that's between this line and this parabola, that's between these two vertical lines, there's actually 3 regions. So there's this one, there's this one, and there's that one. So this was the line x equals negative 8. And so I'm going to have to, as I advance the slide forward, this picture is going to go away. So let me state what's on the next advancing of the slide is that we're going to have an integral that starts at x equals negative 8 and then ends at x equals negative 4. We'll have a second integral that starts at x equals negative 4 and ends at x equals 3. And that second integral is going to have the parabola as the upper and the line as the lower. And then there's going to be a third integral that starts at x equals 3 and ends at x equals 6. And in that third integral, the line is the upper. See, for this third shaded region here, you move up and you hit the line, and you move down and you hit the parabola. Are we okay with, I didn't say for the first integral. There's 3 integrals because there's 3 shaded regions. This first shaded region, it's an integral. I already said the x values from negative 8 to negative 4. I realized, though, I forgot to talk about what's upper and what's lower. The upper is the line, and the lower function is the parabola. Right? So you start in this. I'm going to zoom in here just to make sure sometimes it's a little easier to demo. So in this first shaded region, if you're just like hanging out over here and you move up, then you end up hitting this line. But if you start in this shaded region and you move downward, you end up hitting down here, and this is the parabola. Sorry, I'm trying to thicken this to try to point out where I'm pointing. Okay, so so we've got, I try to point it out in the picture, but just so that this text is here. The first integral starts at negative 8, goes up to negative 4. The next integral starts at x equals negative 4, goes to x equals 3. The third integral goes from x equals 3 to x equals 6. I'd like to, we drew a rough sketch of the picture without showing any axes, but I think it's helpful to point out what it really looks like as well. So there's the 4 provided things, the red line, the blue parabola, and then in black I have the 2 vertical lines. And then this is the region we're talking about, right? You can see really 3 separate purple regions, and you see in this first region, for the first integral, we're going to have the line formula minus the parabola formula. In the second region, notice that it's the parabola that's above. Right? The blue is above the purple shading, the middle purple shading, while the red line here, the red line is the thing that's below. In the third region, the red line is what's above. It's the thing that caps off, and it's above the third purple region, while the blue parabola is the thing that's below. So this is what an integral set up for this would look like. Sorry, it's a lot. Right, but we had this integral from negative 8 to negative 4 of the line minus the parabola, and then the integral from negative 4 to positive 3 of the parabola minus the line, and the integral from 3 to 6 of the line minus the parabola. Why don't I try this? I'm going to just maybe while keeping all of those integrals present and do that. Maybe it's a little Can we see like the first? Let's do the middle integral, right? So the middle integral from -4 to 3. So x equals -4 to x equals 3. The parabola is the one that's above, right? So, and then, but then for this, so that's why there's a 4 minus x squared before the minus sign. Notice in the third and final integral, the 4 minus x squared is after the minus sign because the line is the thing that's above. This line, this red line, y equals x minus 8 is the thing that's above, starting at x equals 3 and ending at x equals 6. I should pause here, see if we're okay with this overall. To some degree, I think one of I think you're all doing all right, but like it's one of these things almost where when you do it, you'll have your approach and your process, and it might look slightly different from mine. So you might be like, why is he doing that? And if you do it your way, just be methodical about your process. You'll probably be all right. Oh, something came in here on this screen though. Let's see. So we. Uh, uh, So all the work we need is just that bottom equation. Yeah, I mean, this is what I would say. Let's say it this way. I appreciate the question. I would say this would be the final answer to this, and find the area. What I usually do so that you don't like so that not all of the points are shoved towards this one kind of question or something. I don't like having if where possible, well, especially during a final, I don't like having a question where it's like you got to do this, and then after you do this part, you have to do this next part, and the previous part has to be correct for the next part to even work. And like, I mean, sometimes that's unavoidable, like with optimization, but like for problems like these, oh yeah, but yeah. So for the answer, yes, the answer I'm gonna say is just this. Like some people might, depending on the expectations of the professor, right? It would be like, oh, you gotta now do the integrals and get down to having a number. But for these questions, just so that it's just, of course it could be done, but these are just annoying. That's all. That, in my opinion, right? So to try to save you aggravation, what I try to do in final exams for 175, I've done it every time, is like you know, just to have you set up integrals. And I try as much as possible to remember to put that in the, I better double check, right, this time around especially, but like to put that into the um, instructions of a final exam question, like right next to where that question is asked to say, just set up the integral, don't evaluate the integral, don't bother, right? Like, and then, but then some other problem where the integral is not as bad, I give a different integral and say, do that integral. Does that make sense? Like I just separate so that like it's just too much for one problem, in my opinion. So yeah, I think a process like this of some kind, again, like maybe here for an in-class setting, I'm adding a lot of extra text. I don't know that anybody would ever really, in exam work would write the sentence, have a line of slope one, a concave down parabola, but that's helpful here. I think probably when I see this, I might think the thing that's in the first point here. I might not, so I'd probably not write this or this, right? But I'd probably show this work. I probably wouldn't write this next block. I'd be thinking it, and I draw a little mini sketch that looks like this, and with vertical line, vertical line. Now that I know where they go, so I crossed out a kind of a number of things here, right? I'd probably, based on the question, I'd probably, as far as showing full work, I'd probably show that. I'd probably draw this picture based on where the intersections are. I'd probably write that, and then I would not be expecting you to evaluate the integrals for a question like this. Evaluating of integrals would be just on its own page of the final exam. It would just be like, here are some integrals, evaluate these integrals. And the only reason I don't want you to evaluate these integrals is because there's three of them. There's three of them. That's all, right? They're not bad, but it's just a lot, you know. I hope that that does it. So maybe give this a try. We got here. y equals x plus 6, y equals 18 minus 2x, x equals 2, x equals 7. Give you a little bit of time. Feel free to ask questions. Think of what kind of curves you have. Are there parabolas? Are there lines? Oh, and while you're working on this, I hope that provided an answer to the question that was asked. I think maybe I said too much almost, right? I think but you let me know if okay, cool. right, so I'd just like to talk through some of the ideas of this question, and I should just note that um, you don't have to think all the same thoughts in the same order as the way I'm going to do it, right? So I think people have their own more natural processes, and you got to do what kind of works for you. Um, but I'll say this for better or worse, as to say something. So the first, just to inventory what we have, there's a line of slope 1, there's a line of slope -2. Um, so that first line has a y-intercept of 6, the second line has a y-intercept of 18. There's also two vertical lines. I didn't mention that in this inventory of the stuff. Um, so yeah, a line of a positive slope with y-intercept 6. So this is my y-axis. There's my 6. There's the 18. So you've got like a slope 1 and you have a slope -2. So this one's the negative sloped one is steeper. But where do these lines intersect, right? Like I kind of want to know that x value before drawing in the vertical lines x equals 2, x equals 7. That's the approach I tend to like to take, because I was like, where do these lines get drawn? You know, is it, if this intersection is between 2 and 7, that's going to be a different picture than if the intersection happened to the left of 2. You know, like all kinds of things could occur. So let's just find where these intersect, set the y's equal. We have this nice linear equation to solve. It's not even quadratic. Add 2x to both sides, subtract 6 on both sides. You have 3x is equal to 12. So x equals 4. All right, that's where the intersection is, huh? So, by the way, the of the two tilted lines, the not the two vertical lines, but of these two lines with kind of more interesting slopes here, the this second line has a y-intercept of 18, right? So that's the one that's going to be above. Like what I'm just in terms of even a rough picture. Let's see, we had y-intercept 6, slope 1, and then y-intercept 18, slope -2. So that's steeper, but sorry, the picture does barely shows that it's steeper. It's not going to matter a whole lot, right? Like we saw this intersection occurs when x is equal to 4, but the whole point is the we're going to set up two integrals, right? Because there's x equals 2, x equals 7. So vertical line, vertical line. So it's like there's this region and there's that region. And the line that starts above is the one that has, well, it had a running start. It started with the y-intercept being 18. And then the thing that we see is right at x equals 4, the two lines switch roles, and then this I wrote it a little differently, but y equals -2x plus 18 ends up being the one that's below once you go past x equals 4. So this should be kind of overall what this looks like. I set up an integral from 2 to 4 of the upper line is the one with y-intercept 18 first. Subtract the lower line is the one with y-intercept 6. Then the second integral is set up starting at x is where the x coordinate of intersection was, all the way up to this provided x equals 7, but then we've swapped which line is above and which line is below. Right? And I do have a picture of that as the next link. Let me just show that just to make sure. All right, so this is, I guess, like that earlier bow tie, but it looks like that bow tie's had a long day. Something like that. I hope that kind of works overall. These take a little getting used to. Again, I think conceptually, in terms of what's the calculus of what's going on and what you need to do from big picture setting, it's not all that bad. The devil's in the details here, right? It's all in the graphing. And I will say this, like we talked through. It's good to be thorough with the ones that we did. Yeah, the big picture in general here is right. Sketch, draw a picture, a rough picture. I mean, at some point, it depends on the problem. You'll be like, I need this part to be more accurate, so you redraw, or you go like, I need the y coordinate here or there, so you find it. You plug in to if you need a y coordinate, you can always plug in, if you plugged in x equals 4 into either of these, you get the same y value, and you can find out what the y coordinate of the intersection is if you need that. We didn't need it here. Um, so you sketch and draw a rough picture, draw a more accurate picture if you need, and then basically, based on your sketch, you're always asking, is one function always above? If so, it's more like yesterday's problem. You only need to set up one integral then. But if not, you might need to set up two or maybe even three integrals. We're not going to do these right now, but I just, in other semesters, I think because of different lengths of explaining and stuff, there are, I provided some problems here. These are all worded a little differently from each other intentionally. There's like enclosed by, area between. Sometimes x values are provided, different wordings. So I would encourage you to try some of these on your own at some point. I will post, so this is a link that goes to nowhere at the moment because I just wanted the slides to be complete, but I will, at where this link goes to, I will upload a PDF that has solutions to all of these, and I think the more thorough I can make them, the better. Or if I can kind of talk through things on paper as much of like, here's what I was thinking about, and here's this y equals root x, that's a sideways half parabola. So I'll try to talk through some of those things. What I want to do is I want to say in maybe 3-4 minutes, I want to talk about what is an application of this stuff. The stuff I'm about to say, you are not going to be responsible for, if you get what I mean, right? Like, it's not going to show up on a quiz or the final or anything like that. Like, normally when I do 175, it is on the final. But we had to cut a week of material, and spending several days on this topic is the thing that unfortunately had to be cut. It pains me to cut it because it's an application, and students I think appreciate applications more than the skills side of math. But like, if I had presented, I want you to think about it. If I present this application without doing the things that we did today and yesterday, I don't think the application would make much sense on its own. So I just kind of want to talk through it, cartoon style. You're not responsible for it, but I think it's interesting. So I think it's helpful to see an application, even if it's not an application you would personally care about. It's one that the professors in the College of Business Administration really want us to cover, and I hope with this brief explanation, you won't be responsible for it again. But like, even with this brief explanation, when you see this in a future class, you'll be like, oh yeah, I did the skills side of it. I'll be ready to go. I'll say this much, that in economics there's this law of supply and demand, and I can't. The point here is not to explain all of that, other than to say that when you put price on the y-axis and you put quantity on the x-axis, as is typical what economists do, sometimes it seems to most of the rest of us, sometimes this seems swapped, but there's a good reason to put the quantity on the x-axis instead. Then if you draw a curve that represents how much people are willing to buy a certain product, that curve is called a demand curve, and it's always it is always hang on here. Wait, see, I'm having issues with this pen. There we go. The demand curve, it's shown here in red, and it always happens to be a decreasing function. It just can't get into it. It has to be. Okay. There's a similar curve for the businesses that are making a certain product, the manufacturers of a particular thing, selling something. And the supply curve, when graphed with price on the y-axis and quantity on the x-axis, that always is an increasing function. And what that means is that these two curves always have to intersect. And they'll intersect in always one place. Again, can't really get into the details of why that works, but if you have a decreasing function all the way through and an increasing function all the way through, they have to just cross each other at one spot. And that spot is called the equilibrium. That equilibrium actually ends up determining, it's the market forces that drive this. And it ends up being that, so at that one point here, this equilibrium, that's what companies like do these calculations first to figure out where that equilibrium is. It's an algebra problem, to be really honest, where these curves intersect. It's like what we just saw. And they decide then, okay, we're going to make this many, what's this this point, they'll get the x coordinate and say, we'll make that many of a thing, and the y coordinate of this point will say that's the price per item. Like that, we shouldn't go any higher or lower. That's what they're going to do. But then there's these regions over here that I want to talk through. So over here, there's this area, so shown in kind of pink, right? And that area represents it's called consumer surplus, and what it really, without digging too much into it, it represents like the area of that ends up being the unit is actually going to be in dollars, and it represents the amount of money that collectively all consumers, all people who wanted to buy a certain product, who ended up buying a product, there were people who were willing, because of the points on the curve up here, there are people who were willing to pay more money for a certain item, but they didn't have to. They only had to pay this much money. And so in total, take all the people who bought a certain thing, and some people felt like they won. They're like, I didn't have to pay as much. I was going to pay more, but hey, it was only going to cost this in the store. And if you take all those people who feel like they really cheat the system, they didn't cheat the system. They just bought the fair price. This area is called consumer surplus. It represents how much the consumers think that they won collectively. And to find that, it's an area of a curve. So it's this curve, the upper curve, minus, and the lower curve is actually just a horizontal line. Right? So this consumer surplus is found as an area between curves. It's an integral from x, or quantity is 0, integral set up to the equilibrium number here, whatever number that is, found from algebra, and then upper curve in red minus lower curve is a horizontal line, right? And then there's a producer surplus that's sort of the same idea. They're producers who were totally willing to sell the product that they made at a very low price, but the market said, no, you should set the price to be that. So they're like, okay, I'll charge more and people are going to buy it. And so there's this region over here. And again, this is an area between curves. And how is it found? Well, it's an integral set up from x equals 0 up to x equals whatever this equilibrium is found using algebra. And the integral is set up with those x values, and then the upper curve now is the horizontal line. The lower curve is the blue supply curve. So we won't do it, but like the point is, in a nutshell, like all of the features are here, and it's an important economic, it's an important concept in economics to talk about producer surplus, consumer surplus, and we have all the pieces in a sense. It'd be too much, like without having 2.5 class days to practice this, no point asking it on the final, so I'm not going to. Tomorrow is Thursday, so please complete the online quiz, and I would suggest starting WebWork 44 today, because if you put it off, the final due date for WebWork 44 and 43 for that matter are both the day before the final exam opens up, so they're both due next Monday. I would just get started on WebWork 44 today instead. But because it is due during finals week, I thought, let's just make it extra credit. So that's what I have for you for today. Final exam will be made available on Tuesday the 12th. Turn it in a single PDF. And see you tomorrow.